Today I'm going to talk about the thinking strategies in the math classroom. PEBC uses 7 thinking strategies to get students to understand how proficient readers read. With that in mind, we're going to talk about how proficient mathematicians think about math. The thinking strategies are: ask questions, activate background knowledge, monitor comprehension, create mental images, determine importance, infer, and synthesize information. Putting a name and example to these strategies will allow teachers and students to communicate more effectively when showing how to solve problems. One of the things I struggle with as a math teacher is how to teach students to problem solve. I never solved puzzles in the typical fashion. I would put the edges on last instead of on first like most people think to do. So I don't normally think or process information as my students would. When I look at the thinking strategies, I like to think about the quote on the screen. The essence of mathematics is not to make simple things complicated, but to make complicated things simple. If I can make my thinking process transparent to students, I have now made the math task easier and simpler for the students to understand. When I was first presented with the thinking strategies, the main thing I noticed was that they had great examples for how they related to reading, but not necessarily things that were as obvious for math. So in the next couple minutes, I'm going to explain how we can make these thinking strategies relatable to math and also to reading. Perhaps the easiest strategy to start with is asking questions. When reading, a proficient reader would often ask questions about the series of events or the character's motive. Asking questions about a theory or hypothesis in math allows us to expand our understanding of the content. When I think about asking questions in a math class, I think about more than just asking about the next step. I often ask myself, why does this process work? Is this the best approach to solving the problem? Is there some information that I can make a connection to that would help me solve the problem faster or in a less complicated manner? Is there a better way to display my answer and communicate my understanding to my audience? As I am asking myself questions, I'm also activating my background knowledge. To activate background knowledge means to use prior knowledge in a new situation or to make connections. When reading Warriors Don't Cry in 7th grade English, students activate their background knowledge of the civil rights movement. In math, a student activates background knowledge by generalizing procedures to new problems that are similar in content. This means that if a student sees a problem that is asking about percents, they might use their knowledge of decimals. Students can also activate background knowledge by applying previous methods in order to find a starting point to solve a new problem. I often have my students do this when working on the challenge exercises at the end of a chapter. When reading a novel, a proficient reader monitors for comprehension by summarizing their understanding as they read. Often in math class, we have not directly taught this skill to students. Students who don't often check their comprehension may get to the end of the assignment and not know why they missed so many problems. To provide a quick method for monitoring their comprehension, I allow students to check answers as they complete problems. This allows a student to find their mistakes or notice what they were thinking when they made a particular mistake. It could also involve making sure an answer is reasonable. Students who monitor for comprehension will often be able to spot their own mistakes before they turn in their final product. As a student monitors their comprehension, they should also be creating mental images. When reading a novel, we often visualize the characters. You can tell people do this when they go see the movie adaptation and remark, "That's not how I pictured it." In math, pictures don't seem so obvious until covering geometry. However, one of the most often used picture types in math is a graph. If students can visualize a graph of the information, then they are creating a mental image. For students who struggle on word problems, I often ask them to draw out what the problem is asking. They don't have to be a great artist for this picture to allow another avenue for understanding the math problem. As you solve a problem, particularly a word problem, you must be able to identify key information. This is best explained by the thinking strategy of determining importance. Often students are overwhelmed by word problems because they normally have irrelevant information. Students who are able to identify relevant information are determining importance. To help students do this, I often suggest that they underline key numbers and circle the question. Students will also use this strategy in math when reading information from a table or graph. When looking at a graph, a student might have to decide if the scale is important or if the independent and dependent variables show a relationship. The remaining two thinking strategies are inferring and synthesizing. These are the two highest order thinking strategies and the ones students and teachers seem to be the most confused about. In order to determine the difference between the two strategies, I like to teach students that inferring comes before synthesizing. When we infer information, we make a guess or prediction about what we think is going to happen. One way that students can do this in a math class is to approximate the answer before making calculations. A student can also infer what method to use to solve a problem, such as substitution or elimination, in systems of equations. This step will normally be connected to at least one other thinking strategy. The last thinking strategy that we have not discussed is synthesizing. Synthesizing information could be thought of as the application of all the other thinking strategies. When a student synthesizes a math class, they are applying what they know in order to generalize a procedure or statement. This might look like students solving a real-world problem and applying their background knowledge of the situation, with what they inferred was the correct procedure, and using those two clues in order to solve the problem. Another place that students could see synthesizing is when a rule or statement is written in algebraic notation instead of in words or with actual numbers. The thinking strategies might not be as obviously visible in a math class as they are in English. However, with simple reminders and application problems, students will be able to use the strategies to become even greater math students. Having students check their thinking strategies allows them to help check their answers.